Mechanical properties of materials. So today objective, student will be able to understand how to measure the stress and strain through experiment, and number two, correlate the behavior of some engineering material to the stress strain diagram. So two things here, one is experiments, one is stress strain diagram. So remember, the stress is force over area and strain is delta L over Li. Alright, tension and compression test. So how we are going to do experiment to determine the stress. Alright, how experiment done to determine the stress and strain. Alright, so let's say we have a specimen. This one we call it as a specimen. Okay, we have this length L naught 50 mm and diameter 13 mm. Alright, so this part, like a threaded part, is the location when we hold or pull this specimen. Alright, or grip the specimen. We want to grip specimen, we grip in this part and also this part. So area that we calculate only this area. Alright, this area is the area of interest. Alright, so this is the machine. We call it as an instrument machine. Alright, so this machine is going to measure the stress. Alright, so we take this specimen and we put into here. Alright, and then we grip both sides, here and here, at this yellow gripper here. So we grip this one and we pull this machine upwards. Alright, we pull this upwards, so it will stretch, elongates. Alright, it will elongates. Alright, so the load here is reading at this controller. Okay, we read the load here. Okay, and the load is measured in Newton. And then what about the elongation? The elongation is using the strain gauge. Strain gauge is we put here. Alright, we put here the strain gauge to measure the how much it will elongates. Alright, this one is same with this one. Alright, so when we pull this way, let's say we pull this way, alright, it will give you readings here, how much is the force and how much is the elongation. Alright, so you get the force, and you get the elongation from this reading. Right, so when you get the force and elongation, you can simply calculate the P of force over area to measure the stress. Force from this and area is pi r squared. R is the diameter of this one. Okay, and the strain using elongation over Li. Okay, so this Li or L naught here. Okay, I put it L naught, yeah, L naught here. Right, is same with here. So delta L is measured from here. Delta L and force. Alright, so tensile test. So one of the most important tests for material strength, The result is found from the stretching of specimen of known size. So known size means how much is L naught and how much is diameter. Alright, so L naught is here, here is L naught, and here is the diameter. Alright, so this is your grip, not counted. This one is your grip to hold this specimen. Alright, so this is the real picture of the how the tensile test is done. This one is gripper up there, and here also gripper, and here is your specimen. Alright, so we come to the stress strain diagram. Right, stress strain diagram. So on this axis we have stress noted with the sigma. Alright, and this axis we have a strain noted with the epsilon. Okay, so this one is stress and this one is strain. Okay, alright, when we pull this specimen, let's say this is your specimen, right? This is your specimen. When we pull this specimen with force P, alright, this is grip. Okay, so let's say at some point it will straight line. What you mean straight line? The stress and the strain are proportional. Alright, in here stress are proportional with strain. Alright, in here. Alright, so stress is proportional with strain. Okay, after some point the stress are same, but the strain are increasing, but the stress are same. Okay, after some point the stress and strain will keep going up until it reach the ultimate stress. The larger value of stress, we call it ultimate stress. Alright, and then it will go down. Okay, the stress will go down, but the strain is going up. The stress will go down until it will fracture. Fracture means it's fail. Alright, broken. Alright, so concentrate with this first. Alright, the below parts. Okay, what is different between below parts and upper parts? For the upper parts, we call it a true fracture. We call it true stress strain diagram. Alright, and this one we call it as engineering stress strain diagram. Alright, so what is different between two is different for the D, the area. This one is D. Okay, this one is your diameter. Okay, diameter. For this one, they use a constant diameter, constant D. Alright, for this one, D is changing. Okay, because when you pull, after sometimes it becomes smaller, right? It becomes very smaller. It becomes smaller. Okay, when we put P, it becomes smaller, so the D here will become smaller. Okay, so D becomes smaller, so the value of stress is also different, because stress is P over A. So in A you have P D squared over 4. Okay, so basically we just concentrate on the constant D. So we assume D is not changing. So this one is, we call it engineering stress strain diagram. This one we call it as a true stress strain diagram. Okay, for the whole parts the D is constant. Alright, for this part D is changing because sometimes, over time the diameter will become smaller and smaller until it break. Okay, so concentrate for the several item. Number one is proportional limits. This one we call it as a proportional, sigma proportional. Alright, and then this one is, we call it elastic region. Why elastic region? If we pull this specimen, we pull here, and then we release, this specimen will going back to the original state. Okay, it will going back to original state, like a spring. If we pull the spring up to this point, it will return to original length. Alright, if we go further, if we pull the load further, it will go like this. So you have the permanent deformation of the specimen. So specimen is no more returned to their original state. Okay, I repeat again. So when your specimen, you give the certain sigma or force until this point, and we release, it will return to this point like spring. Okay, you have specimen. Okay, we pull, you pull with P, and then we release. When we pull, it will elongate some more, right, like that. And then we release, it will return to original state. Okay, this one is for elastic. If you go further, it's no more return to original state. It will become permanent deformation. Okay, permanent deformation. It will not return to the original state. It will become yielding. We call it as a yielding region. This one is elastic region. This one is yielding region. And this one is strain hardening, and this one is necking. Necking means the diameter become smaller and smaller. Okay, so several points. So you have a sigma PL proportional, sigma yield here, and you have sigma ultimate at the top here. We call it ultimate stress. Okay, and you have fracture stress here when it's broken. So remember this 4 or 5 point, 1, 2, 3, 4. Okay, remember this 4 points: proportional, yield, ultimate, and fracture. Okay, just concentrate on this engineering stress strain diagram. It will the most question is come up for this diagram. It's not the upper parts. Alright, so strength parameters. So many engineering material exhibit initial linear elastic behavior where the stress is proportional to strain. Okay, like I said before. So you have a stress and you have a strain, right? So the stress strain diagram is basically like this, up, going up some more, straight line like that, and then it fail. Alright, so this one is sigma yield, we call it. Okay, and then this one is sigma ultimate, and this is sigma fill lah, sigma fill. Alright. So modulus of elasticity, or we call it Hooke's law. Hooke's law is we use in spring basically. Okay, so relation between sigma and epsilon is basically this. Sigma is equals to E epsilon. Same with your spring, we have F is equals to K delta X, right? So same with this, sigma is equals to E epsilon. So E basically is the slope for this one. Slope, okay? Sigma is equal to E epsilon. E we call it as a modulus of elasticity. Alright, like this one. We have a sigma and we have a epsilon. So E is basically sigma over epsilon. Stress over strength is your modulus Young. We call it is also modulus Young. Okay, for the straight region, for the proportional region. Alright. So modulus of resilience measure the triangle area under the stress strain diagram. Okay, so if we draw this figure, okay, so this area, okay, this area, the triangle area up to the elastic region. So this one is UR, modulus of resilience. That's why you have half sigma times epsilon, area of the triangle. Alright, area of triangle. Alright, or we have also half sigma square over E. How we get this? Because epsilon is also sigma over E. Okay, from this parts, epsilon is also sigma over E. You just put in here, you get sigma squared over E. And also you have modulus of toughness, mu UT. Measure the entire area under the stress strain diagram. So stress strain diagram, so entire area is UT, modulus of toughness. Okay, so between these three, the most important is this one, modulus Young, which is the slope for this one. E is equals to sigma over epsilon. We call it as a modulus Young. Okay, higher the value of E, that means the material is more elastic. Alright, so compare with aluminium and steel, still have bigger E compared to aluminium. I think E for steel is 200 gigapascal, and aluminium, E for aluminium is around, I think around 17 gigapascal. Alright, so more value of E is mentioned that material is become high, is become very elastic lah. Alright. Okay, stress strain diagram. When material is stressed beyond the yield point, permanent deformation will occur. Alright, I draw again. This is stress strain diagram. So you have like this, and like that, and then like that. Okay, remember, here is sigma yield, this one is sigma ultimate. Right, so when material is stressed beyond the yield point, so here is your yield point, the permanent deformation will occur. Beyond this, permanent deformation is occur. So this here is your elongation. Alright. Before it's reached here, it will turn back into original state if you release the force. Alright. In particular, steel has region of yielding, whereby the material will exhibit an increase in strain with no steel has region of yielding whereby the material will exhibit an increase in strain with no increase in stress. Okay, that means that steel has region of yielding. The material will exhibit increase in strain here, but the stress remains. Okay, this region where also is called a yielding region of yielding. Alright, if we become larger than this, it will become here. Strain hardening region cause further yielding of material which corresponding to increasing in stress. So this one is strain hardening region. Okay, you call that further yielding of material with the corresponding increasing in the stress. So as the stress increase, the strain is also increased. Alright. Finally, at ultimate stress, a localized region on the specimen begin to constrict, forming a neck. Then fracture is occur. Alright. So you have a specimen like this. Alright. And then it become necking. Necking means become smaller. Right. And then it will fill. And then it will fill. Okay, and then it will fill. Okay. It will fill. Right. So example, you have a data taken from stress strain test. The curve is linear between the origin and first point. Plot the diagram and determine the modulus of elasticity and modulus of resilience. Okay, so you have a stress and you have a strain. So plot this in a graph paper. Okay, if you plot that, you will get like this. Alright, stress and strain. We plot this. You have this graph. Okay, we have so many. We have 1, 2, 3, 4. We have 1, 2, 3, 4, 5 points. So you have 1, 2, 3, 4, and 5 points. Alright, and we plot. So calculate the modulus of elasticity. Modulus of elasticity is the slope for this straight line. So the slope is 224 minus 0 over 0016 here minus 0. So you get the slope. Okay, slope. So you get answer 140 10 to the power of 3 megapascal or 140 gigapascal. Alright. So modulus of resilience is basically equals to area of elastic area of triangle. Okay, area of triangle here. So for area of triangle for the straight line here, just you measure the area of triangle, you get the half 224 times 0.0016, you get 0.79. Alright, Newton mm over mm cube. Alright, you get this. So from this, we can tell that sigma yield is 224 megapascal. Alright, and what is sigma ultimate? Sigma ultimate is at the larger point around here. Okay, let's say that is 280 megapascal. Okay, you can estimate lah. And then the sigma fail. It will fail at here around maybe 270 megapascal. Alright, easy, right? So we come to the another sub topic, which is ductile material. So we have two types. One is ductile material and one is brittle material. Ductile material is, for example, is aluminium, or you have a rubber. Rubber is ductile, elastic, alright. Such as most metal also. Most metal is also ductile. Ductiles mean you can elongate more, alright. There is a bit both elastic and plastic. Plastic means it cannot return to their original shape, alright. When we pull the certain shape, it cannot return to their original. It become permanent deformation. So ductility is usually specified by permanent elongation to failure, or by the percentage reduction in cross-sectional area. Alright. So percent elongation is length of final minus length of initial divided by length of initial times 100%. Alright. So percent reduction area is area of original minus area of final over area of original times 100%. Alright. So let's say you have one specimen, okay, one specimen, we have P, okay, and then it elongates. Sorry. Alright, let's say you have one specimen, okay, and when we put the force, and then it will elongate like this, alright, before it return to the original location, original shape, and then we release, it will return to here. Alright, so elongation, the percent of elongation is basically length of final, this is length final over length of original, okay, divided by length of original times 100. Alright, and also percent reduction of area. When we pull, you have here, and we pull, it become longer, but it become smaller. Alright, so this is your AO, and here your AF area. Alright, area is pi r squared. Okay. Okay, brittle material exhibit little or no yielding before failure. For example, cast iron, concrete, glass are typical example. You have glass, it's brittle. Dalam bahasa Melayu rapuh lah. Okay, rapuh, brittle. So if we put a force here, it will become necking, and then it failure. For ductile material, you have some necking here, alright. For brittle material, is no necking, suddenly it break. Okay, is no elongation, suddenly is, or small elongation, suddenly is break. So rapuh lah, rapuh yang ini tak rapuh lah. It's ductile, this one is brittle. Okay, I think right, I think that's all for today. class. Okay. Okay, I think that's all for this lecture. We continue for next lecture. Okay, thank you. I think that's enough for the today's lecture. For summary, alright. Alright, I think that's all. I think that's all for today's lecture. So for summary, alright. So summary. So we have a stress strain diagram. Okay, this is stress and this is stress strain. So the diagram is like this, and then it's become like this. Okay. Alright. So important points are you have a modulus Young or modulus of elasticity measured as a E sigma over strain for the elastic region. Okay, so this one is your elastic region. Okay, so E adalah slope. Okay, slope of the straight line. This straight line. Okay, so that's the important.